Welcome back to another episode of Practical Electronics and Circuits 101, where I explain the fundamentals of electrical engineering with a focus on practical concepts, which we'll be using for real projects in future videos. Today I'll be giving an introduction to switches and relays. So by the end of the video, you'll have a solid understanding of how to use these components in your projects. Now, it's been a while since I've made a video for this series, and like I mentioned before, I'll be periodically coming back to it with new topics. I'm planning to do a couple more videos over the next month or two, including one on motors and servos, which will lead us into another project I have planned. But today we'll be focusing on switches and relays. So let's begin by giving a general overview of what these components are, how they work, and then I'll do a live demo showing how to control a relay using a Raspberry Pi. Now, I'm sure almost everyone is familiar with how a simple light switch works. It has two different positions, an on and an off position. When it's in the on position, it makes contact between two pins behind the switch. One of these pins is connected to the power source and the other pin is connected to the light. When these pins are allowed to make contact together, this completes the circuit for the light and allows current to flow through it. This switch is the most simple type. It's referred to as an SPST on-off switch. SPST stands for single pole, single throw. Single pole means we're only dealing with a single switch, while single throw means there's only two pins which can make contact together. When the switch is flipped up, these two pins are connected together, and when the switch is flipped down, the connection between these two pins is broken. But it turns out there are more complex switches that can accomplish more complex connections. For example, this one is called an SPDT switch, which stands for single pole double throw. The double throw means there are two different pins that the middle pin can connect to. So when the switch is flipped down, these two pins are connected together, and when the switch is flipped up, those two pins are disconnected, and instead the middle pin connects to the top pin. This is useful in situations where you have two different devices that can be powered, but you only want one of them to be powered at any given time. So the switch is used to determine which device will be on. These switches are commonly referred to as on-on switches instead of on-off, because in this case, both positions are powering something different. Now, the number of throws in a switch can be increased further. For example, here we have a single pole triple throw. Unlike the previous two switches, which only had two different positions, this type of switch has three positions, including a middle position. When the switch is flipped up, these two pins are connected. When the switch is in the middle position, these pins are connected. And when the switch is flipped down, these pins are connected. This type of switch is also called an on-on-on switch, because all three positions create a contact with a different pin. But there are also on-off-on switches, which also have three different positions, but in this case, the middle position doesn't make any connections. But instead, it breaks the other two connections and turns both sides off. But the number of throws doesn't stop at just 3, and it's possible to find SP4T, SP5T, SP6T, and so on. But these types of switches tend to be made in a slide switch format instead of a toggle switch. Slide switches work the same way as a toggle switch, but instead of flipping a toggle, you slide a notch up and down instead. Also, when dealing with these more complex switches, be sure to look at their datasheets to see exactly how their connections are laid out. Now, so far we've only discussed adding more throws to a switch, but what about adding more poles? Adding more poles is essentially the same as adding more switches which are independent from each other. For example, here we have a DPDT switch, which stands for double pole double throw. It's exactly like the SPDT switch I showed a minute ago, but now we have two of them, and both of these are controlled by a single switch. So when the switch is flipped up, these two pins are connected together, and also these two pins are connected together. Each side is completely independent from each other, which means we can turn on two different circuits at the same time. Then when the switch is flipped down, these connections are broken and instead these connections are made instead. Now let's look at a 3PDT foot switch, which works the same as the previous example, but now we have 3 poles, which means 3 separate switches that are independent from each other. In one position, these 3 connections are made, and in the other position, those connections are broken, and instead these 3 connections are made. Now, since this is a foot switch, it uses a latching button that's meant to be pressed by your foot, and these are commonly found in guitar effects pedals. When the button is pressed, it latches down into one position, and when it's pressed again, it unlatches into the other position, and continues to switch back and forth between these two positions each time it's pressed. This means its operation is exactly like an on-on toggle switch or slider. You can also find smaller latching buttons that are meant to be pressed by your finger instead of your foot. In addition to this, not all buttons are latching, and you can also find unlatched buttons which require you to hold the button down to keep it turned on. Now, the other thing you need to keep in mind when purchasing a switch is its voltage and current rating. For example, these little toggle switches can handle up to 125 volts and 6 amps, which means if your house runs on 120 volts, then you can safely use these to control things such as light bulbs and other devices that run directly off AC mains, as long as those devices don't consume more than 6 amps. And generally, it's good to give yourself some headroom, so I'd actually limit this to around 4 or 5 amps max. If you need to handle more current, then you'll want to get a physically bigger switch that can handle the higher demands. So hopefully you have a better understanding of some of the different types of switches and how to use them. So now let's move on to relays. A lot of what I just said about switches also applies to relays, because it turns out relays are also physical switches. But the switches in relays are controlled by a coil, which means we can activate the relay electronically. When the coil is energized, it physically moves the switch inside the relay. And then when power is cut from the coil, this switch flips back to its original position. However, not all relays work like this. There's also latched relays which work more like the foot switch I talked about. With latched relays, the switch remains in the on position even after the coil is turned off, and it will remain latched until the coil is energized again, at which point the switch will return to the off position. And just like all the other different types of switches I talked about a minute ago, relays can also be found in many different formats, including SPST, DPDT, 3PDT, and so on. Likewise, every relay will also have a specified voltage and current rating for what they can safely handle. Now, like I just mentioned, the advantage of relays compared to regular switches is that we can electronically control them from other devices, including microcontrollers and SBCs. But the output pins on these devices can't supply enough current to activate the coil in a relay, which means we need to use a transistor that can provide enough current. The microcontroller's output pin activates the transistor, and then the transistor activates the relay. But if you know anything about transistors, or if you saw my previous video on transistors, then you know that transistors themselves can be used as switches. So you might be wondering what the differences are. Certain applications will require only transistors. Other applications will require relays, and in some applications, either one can be used, but there are trade-offs with each one. The main problem with transistors and applications where you need to power other devices is that transistors aren't 100% efficient, which means you'll be wasting power in the transistor itself. And not every transistor is able to handle high-powered loads either. The transistors that can handle higher loads can be fairly expensive, so cost becomes a factor as well. Relays, on the other hand, don't have any problems with efficiency. Once the relay is activated, it creates a physical connection from the power source to the load. This connection is low resistance, which means efficiency is nearly 100%. and this can be a big deal in applications that use a lot of power. So in applications where you're dealing with high-powered devices, or in cases where you're not sure how much current will be required, you'll probably want to use a relay for those. Also, relays don't care what type of signal they're dealing with, as opposed to transistors, which are DC-only devices. The only way a transistor can handle AC signals such as audio is if the signal is biased first before going to the transistor. But a single transistor cannot handle both positive and negative voltages, which means it can't handle your house's high voltage AC mains. For these applications, you'll need to use a relay. But of course, there are pros and cons to everything, and relays have their own limitations. One of the biggest limitations in relays is that they can only be on or off. There's no in between, as opposed to transistors, which can deliver a variable voltage, and this voltage can be easily controlled as well. Another limitation in relays is that they're relatively slow. So in cases where you need to switch a signal on and off extremely fast, which is common in digital systems, then you'll need to use a transistor. Also, since relays are mechanical devices, this means they can wear out. Every relay has a rating of how many times it can be switched on and off before it becomes unreliable and needs to be replaced. But as long as you don't exceed this number, relays are incredibly resilient and they can handle a lot of abuse. Another application where you'll find relays are in audio systems and amplifiers. For example, many high-end guitar amplifiers contain multiple channels, and relays are a common method used to switch between channels. But it's also common to see other methods being used, including transistors. So this is an application where both relays and transistors are acceptable, and it comes down to personal preferences and the trade-offs between both devices. For example, since an audio preamp signal is low power, power efficiency is not a concern with transistors in this case. And since relays require power to energize their coil, this is actually a scenario where power consumption will probably be lower by using transistors instead. There are a number of other applications where you'll find relays, but the examples I just mentioned should give you a general idea of how they're typically used. So now let's talk about how to use a relay and how to activate its coil. Like I mentioned earlier, when controlling a relay with a microcontroller or SBC, you'll need to use a transistor to provide enough current to the coil to activate it. But every relay will also have a specific activation voltage, which can typically range anywhere between a few volts up to several dozen volts. This is also referred to as the coil voltage. For example, this is the relay I'll be using for the demo in a minute. It's a Songle SRD03VDC SLC. The 03VDC indicates that this relay's coil voltage is 3 volts DC, but you can also find the same relay with other voltages. For example, the SRD05DC has a coil voltage of 5 volts, and so on. Here's a list of the different models from this family of relays with coil voltages up to 48 volts. Again, all these models are exactly the same except for their coil voltage and the required current. The higher the coil voltage, the lower the current requirement is. You'll also notice there's high sensitivity variants which have lower current requirements than the standard ones. Now, since I'm using the 3 volt variant, this one requires the most current at 150 milliamps. This means the transistor I choose needs to provide more than that. If you haven't seen my previous video on transistors yet, then I highly recommend seeing it since I'll be talking about concepts from that video. In that video, I showed how to use BJT and MOSFET transistors. The BJT transistor I used was a 2N3904, which was used to power several LEDs. The maximum current for this transistor is only 200 milliamps, which is enough to power this coil, but it's not a good choice overall. Like I explained in the previous video, BJTs are more difficult to implement than MOSFETs, because BJTs are current-controlled devices. which means you need to carefully select the base resistor value to make sure the transistor is delivering the desired current. But the real issue here is that since we require 150 milliamps, this means the gain factor for this transistor is extremely poor at such high currents, and we might run into a situation where the Pi's output pin can't deliver the necessary current. This is a situation where you'd want to use a MOSFET transistor instead. Not only are MOSFETs more power efficient, but they're also easier to work with, and we don't need to worry about a base resistor since these are voltage controlled devices, not current controlled. So for this example, I'll be using the 2N7000 transistor, which is a low powered MOSFET that can deliver up to 200 milliamps. Now the other thing I should point out is that this particular relay, along with all the other versions here, contain an SPDT style switch, which means we have a common pin, an NC pin, and an NO pin. When the relay is off, the common pin is connected to the NC pin, and when the relay coil is energized, the common pin will disconnect from the NC pin and connect to the NO pin instead. Now, if we look at the bottom of the actual relay, we'll see some markings to indicate which pins are which. The coil here indicates that these two pins are connected to the coil. The middle pin is the common, this pin is the NC, and the last pin here is the NO pin. Alright, so now let's do a hands-on example and control a relay with a Raspberry Pi. If you haven't seen my Raspberry Pi playlist, then I suggest watching that as well if you need help setting up your Pi. Also, this written guide I have on my website goes into detail on how to use the GPIO pins in Python programs, which is how I'll be controlling the relay. The links to the guides and playlist are in the video description. I'll also include the link to these relay module boards on Amazon, which already contain the transistor and other components directly on the board. The relays I have are the same as these, except they're just the bare relays without the board, which means I need to build the transistor circuit on a breadboard. Also, like I mentioned earlier, the ones I have are 3-volt variants, while the module boards are 5-volt variants. But as I'll explain in a minute, either of these will work fine with the Raspberry Pi. So I'll first show how to connect everything on the breadboard like I did, and then afterwards I'll show how to connect everything using these module boards instead. So here's the complete schematic. The relay is the symbol right here, and on the left side are the pins for the coil. So let's start there. Since this is a 3-volt coil, I've connected one side directly to the 3.3 volt pin on the Raspberry Pi. If you were using a relay with a 5-volt coil, then you'd want to connect it to the 5-volt pin on the Pi. And it's actually preferable to use a 5-volt relay here because there's more current available on the 5-volt rail. The Raspberry Pi contains a regulator for the 3.3 volt rail, but this regulator can only provide up to around 500 milliamps on most Pi models. The original Pi actually had a much lower limit of only 50 milliamps. But the original Pi is already 10 years old now, so I imagine most people would be using a newer model with the higher limit. But 500 milliamps still isn't a lot, since each relay can use up to 150 milliamps. So you're only limited to using 2 or 3 relays maximum. But the 5-volt rail on the Raspberry Pi doesn't have a limit, since it's connected directly to the power supply. So the maximum current is directly determined by how big your power supply is. So generally speaking, I recommend using 5-volt relays with the Raspberry Pi. The reason why I'm using 3.3 volt relay is because that's what I had lying around. But anyway, let's move on. Now you'll also notice I have a diode connected to both ends of the coil. This is a shoddy type diode, and the specific model I used is a 1N5817. Diodes are necessary when charging and discharging coils. Like I've explained in a previous video, the magnetic field around coils can create a reverse current when the coil discharges. This can damage the transistor in certain scenarios, so you'll want to make sure you include this diode for protection against that. and make sure you orientate it like you see here. Next, we have this side of the coil connected directly to pin 3 of the 2N7000 transistor. Pin 2 of the transistor is connected directly to one of the Pi's output pins, and pin 1 of the transistor is connected to the Pi's ground pin. We also have this pull-down resistor here, which is necessary to make sure the transistor doesn't activate by accident. Now on the other side of the relay we have the NC, COM, and NO pins. In this example I've connected a separate 12-volt power supply to the common pin, and then connected a 12-volt LED strip to the NO pin. I placed two LED symbols here to represent the LED strip. So just to be clear, don't try to connect two individual LEDs to 12 volts, since they'll likely fail. The other side of the LEDs are connected to the 12-volt power supply's ground. When the relay is activated, it'll make the connection between the COM and NO pins and allow current to flow through the LED strip. When the relay turns off, it'll break this connection and go back to its default state where the COM pin is connected to the NC pin. If you wanted to power something when the relay is turned off, then you'd simply connect that device to the NC pin. Now this is a simple example using low voltage components, but if you wanted to power high voltage components such as light bulbs or other devices that run directly off the AC mains of your house, then the wiring would be exactly the same. Here's an example of how you'd connect a light bulb. As always, make sure you're extremely careful when dealing with high voltages since touching live wires can result in serious injury. So now let's go over how to connect the module board that's available on Amazon. On this side we see the NO, COM, and NC pins, and these are exactly the same as how I just showed. And on the other side we see DC+, DC-, and in. For DC+, you'll need to connect this to the Pi's 5-volt power pin. Again, these relay boards contain a relay with a 5-volt coil, so you'll need to use the Pi's 5-volt power pin. Now DC- is connected to the Pi's ground pin, and the in pin is connected to the Pi's GPIO pin. And that's all there is to it. These boards make everything a bit easier. Alright, so now let's see it in action. Also, something I should mention is that the way the pins are orientated on this particular relay make it incompatible with breadboards. So that's why I've connected it like you see here. I soldered some solid core wires to the coil pins so that I can connect them to the breadboard. I also soldered a red wire to the COM pin, which is connected to the 12-volt power supply. And then I used alligator clips to connect the LED strip to the relay's NO pin. Now let's go to the GPIO guide that's on my website and scroll down to the first example that I did there. I use this code to simply turn an LED on and off once every second, and I'll be using this exact same code for the relay. So now let's run it. And as you can see, it's working as expected. The LED strip is blinking on and off once every second. I'm not sure if you can hear it or not, but every time the relay turns on or off, it also makes a clicking noise. So you actually don't need to connect an LED or anything to verify that it's working, since you can hear the switch clicking inside. And that's really all there is to it. Controlling a relay is really just a matter of controlling a transistor which activates the relay's coil. Now, something else I wanted to point out is that Amazon also has these large multi-relay boards for applications where you need additional relays. Some examples are this 4-channel board, an 8-channel board, and even a 16-channel board, so there's plenty of options. Also, pay attention to the voltage that the relays run at, because some of these boards contain 12-volt relays, which means if you want to use it with a Raspberry Pi, then you'll need to use a second power supply running at 12 volts for the transistor. Alright, so that pretty much covers everything I wanted to go over on switches and relays. Hopefully now you have a good understanding of how to use these components in your projects. Like I mentioned earlier, I'm planning to do another video that covers motors and servos, which will lead us into the next project I have planned, which will involve motors. So stay tuned for that. If you have any thoughts or questions, then feel free to drop a comment, and if you found this video to be helpful, then be sure to give it a thumbs up and subscribe to the channel if you haven't already. Thanks for watching, and I'll see you next time.